So in the previous videos, we looked at inertial and viscous scaling. And in those cases, we sort of knew what the scale for time and pressure was based on some arguments. What I want to show you here is more of a general way that can be done, that can be applied to the Navier-Stokes equations, but by not specifying the scale a priori, rather determining the scale based on scaling arguments after the dimensionless equation has been derived. And so because the continuity equation doesn't change, what we're going to do here, we are going to start directly with the momentum equations. And so we would have rho du by dt plus u dot grad u is equal to minus grad p plus mu del squared u plus rho g. And we will introduce the following scales. We're going to say that x is, or x star is x over L0, which is some characteristic scale that is typically known in the system. Sometimes you could choose this to be a diffusive length scale, and that is going to also depend on the problem. But here we're going to assume we just know what L0 is. And for time, we're not going to assume anything for time. We're going to say that T star is equal T over T0, and T0 is to be determined. For the velocity, we will say that U star is U over U0. And for the pressure, we're going to define P star as P minus some P infinity over a delta P, also to be determined. So previously, we made the scaling arguments such that delta P over rho V squared, for example, was equal to 1, or delta P over the viscous scale was equal to 1. We're not going to make that assumption here. We're just going to leave this term stand on its own merits. And then we've also shown that nabla was equal to 1 over L0 nabla star, and nabla squared was equal 1 over L0 squared del squared. And so with these changes, we can go ahead and put these into the equations, and we forgot gravity. We're going to say that G star is equal to G over G, okay? And with these changes, we will have rho times du by dt is u0 over t0, du star by dt star. I know the stars can be annoying. One other way I suggested is to write the dimensional equations with stars and make the dimensionless form unstarred. In event, we would have plus rho times, we have a u0, so we get a u0 squared over here over L, because grad is equal 1 over L0 grad star, and we get u star dot grad star u. And for the pressure, what we will get is minus, we'll have a, so P infinity is not going to be affected by the gradient, so that disappears. So we get minus delta P over L0 grad star P star plus mu u0 over L0 squared del squared u plus rho g star. Okay, so now I didn't do anything to T0. Now what I want to do is make all of the coefficients in this equation, make them dimensionless, and that is entirely possible. And the way we're going to do this is start by looking at this scale. So this is u. So if we can get rid of the density first, we take the density, divide by the density. This would give us, so we divide by the density, and this would give us a rho over over here, and a rho over here, and rho over rho will disappear. And then for this u0 over t0, so this is meters per second over a second, so that gives us meters per second squared. What we would need is to turn this into a dimensionless term. So if we multiply by L0 over u0 squared, that would give us L0 over u0 times t0. So think with me for a second here. We have u0 over t0 in terms of units. That's meters per second over second, and that's meters per second squared. So we need to multiply by second squared over meters, okay, to make this dimensionless, to make this term, this quantity dimensionless. So if we multiply by L0 over U0 squared, so all we have to do is multiply by L0 over U0 squared. So what we get is L0 over U0 squared times U0 over T0 du by dt. So quantities are stored. This guy turns into 1. U dot grad u is equal to minus, we have an L0 over U0 squared, correct, times delta P over L rho L0 grad P star plus L0 over U0 squared times mu U0 over rho L0 squared del squared U and plus L0 over U0 squared times G star. So what happens here, this term, let's use green, so this term becomes, so we can cancel out U0 and U0, and this term becomes L0 over U0 T0. Now, this is actually a dimensionless quantity, and that quantity is known as the Strouhal number. If you think of 1 over T0, that's a frequency, right? And the Strouhal number is defined as FL over U. And with that frequency definition, we can turn this into a Strouhal number. So that is equal to the Strouhal number. Now, why does this matter? Why would we keep T0 as is and not use a velocity scale like L0 over U0, for example? Well, what if you have some time-dependent boundary conditions that are whose scale or the frequency by which the inflow is changing is much smaller than the L0 over T0, so you'd have to choose that as the time scale. Or if you have vortex shedding, for example, or some oscillatory behavior in the flow that you need to account for, then you would choose that time scale, and that would give you the Strouhal number. But for steady cases, the Strouhal number would be typically 1, or for a steady state case, it would just be very, very small, so that would kill this time-dependent term. And this is a great way to generalize the equation, and we will see how we can say, later on, we can compare terms and say if the transient term is important, then Strouhal number needs to be 1, and therefore T0 needs to be equal to L0 over U0. Okay. Now, what about this term over here? So L0 and L0 cancels out, and then you get a delta P over U0 squared. We haven't chosen what delta P is, but this quantity, this whole quantity, is actually a dimensionless number, and that is equal to the Euler number, which is equal to a pressure difference over rho U0 squared. Now, depending on the type of flow, again, we're going to make an argument later and say, hey, the Euler number needs to be equal, needs to balance the Reynolds number, and 1 over the Reynolds number, for example, and then therefore delta P needs to scale with the viscous scaling. So without having to think about what scale to pick for delta P from the outset. Okay. Now, what about this guy? We get L0 cancels out with L0 over here. U0 cancels out with U0. And what we get here is the mu over rho U0 L0, and that is 1 over the Reynolds number, which is mu over rho U0 L0. Okay? And this guy L0 G over U0 squared, that is 1 over the Froude number squared. And then we get a much more general equation or dimensionless form of the Navier-Stokes equations without having to specifically choose T0 and delta P. We will choose those based on the physics. Once we get the physics in, we're going to say this term is, one term is going to be dominant over the other, and then we'll be able to make the arguments that make the dimensionless numbers appropriately scale the different terms. So with that being said, we have a Strouhal number times du star by dt star plus u dot grad u equal to minus the Euler number grad p plus 1 over the Reynolds number del squared u plus 1 over the Froude number squared g star. And that will give us the unsteady, dimensionless Navier-Stokes equations. We haven't chosen the time and pressure scales yet so that we could say that the terms will be comparable. We're going to do that after we make judgment calls on the physics. So let's see now how we can, from this equation, derive some of the different cases that we have shown earlier. So we will start with the Inviscid equations, and I'm going to write the dimensionless equation here again. Strouhal number du by dt. I'm going to drop all the stars. Plus u dot grad u, all of these quantities are dimensionless, equals to minus the Euler number grad p plus 1 over the Reynolds number del squared u plus 1 over the Froude number squared g. Okay, so now for inviscid flows, or flows where viscous effects are negligible, very high inertia, as the Reynolds number approaches 0, then, as the Reynolds number approaches infinity, then this term becomes vanishingly small as Re approaches infinity. And then, therefore, we have a balance between the remaining terms. If we further assume that the time scale, or the Strouhal number is 1, so then we can drop the Strouhal number in front of du by dt, or you can keep it. But now what is very important here that I want to stress out is the balance of the terms. So if you say that grad P, the pressure force, this term, needs to balance with convection, it's as strong and important as convection, it's not negligible, then the only way this could happen is if you want Euler grad P to be of the same order of u dot grad u, and that's how you do it. You balance two terms at a time. Then this necessarily implies, so if this guy is order 1 and this guy is order 1, this necessarily implies that Euler is order 1 and assumed to be equal to 1. So this means that delta P over rho u0 squared is equal to 1, and therefore your delta P is equal rho u0 squared. And that's what we did in the first time when we chose the scale for delta P. We said, let's make delta P over rho u0 squared equal to 1. Now, the motivation is that you think that pressure forces are going to be as important as advective forces. There's no reason for them not to be as important as the remaining forces. And you can make the same argument for the du by dt term. You could say, well, there's a missing scale over here, so I'm going to compare this term to another term where there is a known scale. So you could, for example, compare this guy to that guy, and then you get a time scale related to the Froude number. Or I would say just take this Strohal number. If this is it's just standard unsteady flow where you have du by dt comparable to the advective term, then you would say that very simply Strohal du by dt is of the same order as u dot grad u, or the same importance. This implies that the Strohal number is order 1, and we assume it's equal to 1. It's just a constant. And then that implies that L0 over U0 T0 equal to 1, and therefore T0 is equal to U0 over L0 over U0. Sorry, L0 over U0. Okay, and that's how you get the Euler equations. You would say du by dt plus u dot grad u is equal to minus grad p. You could do the, now the Froude number, there's not much you could do there because that already has a length scale which we had defined appropriately, and gravity you have no control over, and u0, and so you would leave this term as is. And this is a very powerful way of deriving these specialized equations. Now, what about the other case when the Reynolds number approaches 0? So again, we take the Strohal number du by dt plus u dot grad u is equal minus Euler number grad p plus 1 over the Reynolds number del squared u plus 1 over the Froude number squared g. Now, I told you earlier that when we did the inertial scaling, you couldn't just multiply by the Reynolds number because we had already assumed a scaling for grad p. But in this case, we can, because grad p is independently controlled by the Euler number. So if Re approaches 0, let us multiply by the Reynolds number. Okay, so what do we get? We get Reynolds Strohal du by the dt plus Reynolds u dot grad u is equal to minus Reynolds times the Euler number grad p plus del squared u plus Reynolds over Froude squared g. This is interesting. As the Reynolds number approaches 0, we are saying that we already said that the beauty of the dimensionless and normalized equations is that we can assume, at least at some point, that all of the derivatives are all of order 1. And the only way to change and rescale the strength of a quantity is through the dimensionless parameter. So if u dot grad u is order 1 and Reynolds number is order 0, then this guy becomes negligible as the Reynolds number approaches 0. So we get rid of the convective term. Then this whole thing is the dominant term over here. But what do you want it to balance with? We can make it balance with gravity. So we can make the Reynolds number over the Froude squared remain, or if this Froude squared is order 1, then we can neglect this guy because the Reynolds number is so small. Okay, so we can neglect this term. What about this term, Reynolds Euler? If the Reynolds is small and the Euler number is like order 1, then we can probably drop this term, but that doesn't give us much because we really need a pressure force to be involved in this flow. And the only way for this to work is if Reynolds times Euler is equal to order 1, which is equal to 1. So we say that the Euler number scales with 1 over the Reynolds number. Now remember that we can do this because there's a missing scale over here. And the Euler number is delta p over rho u0 squared. And we're going to set that equal to mu over rho u0 L0. Now what that tells us is that delta P is equal to mu rho u0 squared over rho u0 L0. If we knock out the common terms, rho and rho, and u squared, and that gives us our viscous scaling. Delta P being equal to mu u0 over L0, just like we did before. And that makes this entire term equal to 1. Now, what about this term? You could do the same thing. So if you want this term to disappear, steady state, then it disappears. Strohal number is order 1, then Reynolds number is so small it's going to knock out this term. Or you can still do an unsteady Stokes flow, and by making the same exact argument, saying that Reynolds times Strohal is order 1, so that makes, we can do this because there's a missing scale in the Strohal number, which is T0, which makes the Strohal equal to 1 over the Reynolds number, and that means, so remembering the Strohal number as being L0 over U0 T0, so that's L0 over U0 T0 is equal to mu over rho U0 L0. This implies that, so we want T0 from this, so we get an L0 squared times rho U0 over U0 mu equal to T0, and you get rid of the common terms, and what you get here is a viscous timescale, T0 equal L0 squared over nu, which is a viscous diffusion timescale. And this is really cool because you may not have guessed that from the beginning when you chose the timescale, and that gives you an unsteady Stokes equation. So this guy is 1, that guy is 1, this guy disappears, and we can neglect this guy, okay, because we don't really have a missing scale in the Froude number. Unless you are looking for a length scale, for example, you could probably determine that from the Froude number. But the point is that you have many options based on your reasoning and how you want to manipulate this, this particular equation. So then with these scalings, we would have an unsteady Stokes flow, du by dt, okay, E plus grad P is equal to del squared U. And for steady state, of course, that gives us the Stokes equations, but you can add an unsteady term as well. And what this says is that all of these guys are actually balanced, or taken kind of two at a time. They're all of the same order, at least in some part of the domain, until your assumption breaks. Okay, until your assumptions break, then you would need to include all the terms. So if you left all the terms in the equation, it doesn't matter. Okay, it does not matter. But the reasoning behind scaling is that if you choose the proper scales for the problem, then you can reasonably assume and assure that different terms you can balance every two terms together, and then you can choose your characteristic scales in a way appropriately. And if you do that, you get the appropriate governing equations for your flow.